First of all, thank you very much for the invitation and the opportunity to give my personal view of the future of contact thermometry here. Okay. Okay. Historical notes. Let's start with Pierre Chapuis. He worked at BIPM in the 1880s, 1890s until 1900, and he was a famous person for gas thermometry. So he worked with a gas thermometer. Here you see a picture of it, and he established the first temperature scale on gas thermometry using hydrogen. So very beautiful and pioneering work in that field. And you can see here, he also continued his work with gas thermometry and made a comparison with platinum resistance thermometry. He compared it with his gas thermometer, and this work was done together with Jonathan Harker from a forerunner of NPL. So, and if you look at what you see here, this platinum resistance thermometer, this must be very familiar to many of you. So it's very similar to what we have today in platinum resistance thermometry. So this was really a pioneering work. At that time, he continued working on gas thermometry. 1903, he performed new measurements on gas thermometry, and finally, in this work, he also determined the boiling point of sulfur. So this paved the way to what we have today, the ITS, and based on fixed points. So, and just to emphasize a little bit more how beautiful the work was, can make a comparison at 50 degrees Celsius from the hydrogen scale going over to different ITSs to now what we call thermodynamic temperature. And starting in 1999, the normal hydrogen scale was established, and there was no difference to the ITS 27. There was also no difference to the ITS 48. And the first difference was minus 10 millikelvin from the hydrogen scale to the ITS 68, then came to minus 23 millikelvin, and back, if we compare it now to the latest thermodynamic temperature measurements, we have minus 16 millikelvin. So this is the overall difference between the hydrogen scale and thermodynamic temperature, and that emphasized once more that this was really a beautiful work, and chapeau, chapuis, or let's say well done. Okay. Even though the experimental part was very well established, at that time the theoretical part was not so well, let's say, not so well accepted. This can be seen from a discussion between Boltzmann and Kelvin in 1895, where Kelvin wrote a letter to Boltzmann stating that he makes absolutely no progress towards comfort or happiness in regard to it. With it, he meant the Maxwell-Boltzmann distribution. That means he was not very happy with the statistical view of Boltzmann, and but he was clearly accepting that this is the main problem, or was the main problem of temperature of thermodynamics at this time. Okay, now a little bit, a few words about the way to the actual definition. So the former definition, we all know it's via the triple point of water. This was an idea from Thomson, or later Lord Kelvin, in 1854. So together with Joule, we worked on the Joule-Thomson effect, and we stated in their work that it is possible to fix the temperature unit by simply fixing one point, and he mentioned the ice point. We all know that at the end we have chosen the triple point of water. And if you know the isotopic composition and know something about the impurity content, we have typical uncertainties in the realization of this fixed point on a level of 30 microkelvin, relative 1 to the minus 7. And this is incredible, and this is the reason why it was lasting so long, this definition. From a theoretical point of view, surely the idea of Boltzmann was favorable. So if you look at an ideal gas, and when you increase temperature, the mean velocity of a particle increase, And this makes clear that temperature is always connected, or thermal energy is connected to kinetic energy. If you make a direct link, you would have temperature in terms of joule, very small numbers here, 10 to the minus 20 up to 10 to the minus 6. So we're not used to that number, so we need a conversion factor, which is the Boltzmann constant, and then we have these units in Kelvin, and this clarifies that the Boltzmann constant is simply a conversion factor between energy and temperature, and fixing that value fixes the temperature unit. Okay, so here you can see the three primary thermometers mainly contributing to that, to the work before the redefinition. So it's acoustic gas thermometry, measuring the speed of sound of a gas, dielectric constant gas thermometry, measuring the dielectric constant, and Johnson noise thermometry, measuring the mean square noise voltage along a resistor. So with these three methods, determinations of Boltzmann constant have been performed, and this is the final score. At the end, following a recommendation of CCT from 2014, it was necessary to have at least one determination below 1 part per million uncertainty and at least another fundamentally different method with an uncertainty less than 3 parts per million. So this was successful, as you can see here. So we have acoustic gas thermometry, different determinations of acoustic gas thermometry, we have dielectric constant gas thermometry, and Johnson noise thermometry. And this allowed a sound definition of a unit. This was performed last year, as you all know, and it switched from the philosophy of Kelvin to the philosophy of Boltzmann. And today we have this definition of the Kelvin. Okay. So now the actual status. If you want to learn more about the actual status, you can go to the BIPM website. You can download the Mise en Pratique, and one part of a Mise en Pratique is, there are these descriptive documents, the scales, PLTS 2000 and ITS 90, and the SI definition. And a new part is now here, mainly here in this, that we have primary thermometry included in a Mise en Pratique. And this will be the focus of my talk now. But one slide will be left for the ITS 90. It's important to emphasize that the status of the ITS 90 is unchanged, even though we have a new definition. This is quite clear. As an intensive quantity of temperature, we always need a definition. This was the triple point of water. But we always need fixed points, different fixed points. These fixed points have been determined by primary thermometers in the past for establishing a temperature scale. And the only thing that changed now is that the triple point of water will lose or has lost its double meaning. So now it's one of the other fixed points of the ITS 90. And very, very important, because there's a lot of discussion, is that we have no uncertainty associated to all of these fixed points in the ITS 90 with respect to the respective scale temperature. So this is what I wanted to say to the ITS 90, and now I will focus on primary thermometry. So what is a primary thermometer? It's based on a well-understood physical system, and you need an equation of state without unknown constants. Okay, so this is the definition. So we need the criteria for primary thermometer is a well-derived equation of state, a complete uncertainty budget approved by CCT, an uncertainty acceptably small. At least we need 2 independent realizations, comparison with results already of accepted methods, applicable over acceptably wide temperature ranges, last but not least, detailed documentation in open literature. So these are the criteria for primary thermometers. And I showed you already 3 of these primary thermometers. They are already included in the Mise en Pratique, and there is one primary thermometer left. This is refractive index gas thermometry. You can see that from the equation of state that they are very similar. Dielectric constant gas thermometry and refractive index gas thermometry are very similar. Therefore, we have included it as what we call now polarizing gas thermometry. So they are combined. So at the end, we have 3 completely different primary thermometers here. So if we talk about realization and dissemination of a temperature unit, we always have to take into account the uncertainties connected with that. And here you see a plot of the uncertainty of thermodynamic temperature measurement and the uncertainty of let's say the best realization of the fixed points. And in most cases, you see almost a factor, an order of magnitude, larger uncertainties at the moment connected with thermodynamic temperature. So that clarifies that at the moment, it's not, at least in the core range of ITS-90, it's not possible to have a direct realization of thermodynamic temperature and doing calibration work. And the best check, and this is at the moment the best performance check we have, is the plot I showed you before. This is the final score of a Boltzmann measurements, and we can now turn it the other way around and compare it against the triple point of water. This is done here. So this is a plot now against the accepted value for the triple point of water, and the green bar here is the realization uncertainty of a triple point of water. So this clarifies once again that ITS-90 in this range is much more powerful than thermodynamic temperature measurement. But what is very important is that the actual best access to thermodynamic temperatures now via T90 calibration and using the estimates T minus T90. And this is the way the users have to follow for a good estimate of thermodynamic temperature. And this clarifies once again that now T minus T90 becomes more and more important. You can see it here. So these estimates gain importance now. Okay. I'll come to the next steps. This is a picture of working group 4, the deviation T minus T90 over the temperature range from 0 to 1000 Kelvin. So as I said, in 2011, and I've been performed a lot of work in the last years, especially in the low temperature range, to improve the uncertainties here and the estimates. The latest improvements are here now summarized in the range from 30 Kelvin to 200 Kelvin, from the acoustic gas thermometry from NPL, refractive index gas thermometry from NRC, and dielectric constant gas thermometry from PTB. And just to check, we have summarized here the work of these 3 primary thermometers, and the gray area is the former working group 4 estimate, and the red area is now the summary of these 3 primary thermometers. And as you can see, that the uncertainty is reduced by almost a factor of 4. So this is the way we have to continue. But we have further new data on T minus T90 from acoustic gas thermometry in a higher temperature range here from INRIM. Also in a higher temperature range here from NIM, from NEF3, and for NNIJ. So this has to be included as well, and also from polarizing gas thermometry here with a relative primary thermometer, and from LNA and CAS in this case, and in the low temperature range here from INRIM, from refractive index gas thermometry. So the next step of our working group will be that we have to agree on new consensus values from 4 Kelvin to 303 Kelvin. That will be the next step. So we should have an estimate with the new let's say mean value of these 3 primary thermometers. We have an estimate what might be the outcome, but at the end we'll need all the data from polarizing gas thermometry, all the data from acoustic gas thermometry, and I can combine it to a new consensus value in the low temperature range with a very largely reduced uncertainty. So this is a very near future. Now to the perspective. I showed that before, but especially the higher temperature range for contact thermometries at 600 Kelvin is really a problem. So we have large discrepancies and large uncertainties as well. And in this range, we urgently need new data on T-minus T90. And therefore, a suggestion for the discussion would be that we have a new recommendation here from CCT that we require new determinations of thermodynamic temperature above 400 Kelvin. That would help to put the finger on this problem. I will show it on the next slides that this is really one of the key problems for contact thermometry. So what we further need to improve and to implement the new Kelvin is that we have to perform direct comparisons of primary thermometers, not at the triple point of water, as has been done within the Boltzmann project, but now with at the low temperature end, it's always discussed between INRIM and PTB that we will have a dielectric constant gas thermometer together with inner crystal together with a refractive index gas thermometer. And the good thing about refractive index gas thermometry is that you also can include easily a few microphones, and then you have also an acoustic gas thermometer. So these three primary thermometers can be compared in one apparatus. That would be very helpful. But already mentioned, the temperature range above the triple point of water is one of the main problems. And here we can think about comparisons between acoustic gas thermometry and Johnson noise thermometry. We need volunteers here in this range. I know that NPL is doing acoustic gas thermometry within European projects in a high temperature range, but there are other institutes like NIM, like NIST, with a lot of knowledge on these two primary methods, and maybe we can have here a direct comparison. So also we need an inclusion of new primary thermometers. Therefore, CCT have a task group of emerging technologies, here, one of the candidates is the Doppler broadening thermometry, measuring the Doppler width of a laser going through an absorption cell. This method has also been involved in the Boltzmann project already. So I think they are very close to be included, but still there are some problems to be solved. First of all, the temperature range of applicability, the mathematical description of a profile, and other things. So it's very important that this task group works on these problems, and then we can include that in a mise en pratique. So this is already one of my final slides. This is here a midterm perspective. At the moment, surely the balance is on T90. If we talk about the transition from T90 to TXX, we have to emphasize that T90 is a well-implemented system with long-term experiences, and especially all the actual demands are met. So on the other side, we have to talk about substitution of mercury, and now we have new data on T-minus T90 in the low temperature range. But for a real transition, the criteria must be that we need small uncertainties in the complete temperature range of contact thermometry, T-minus T90. This is the main point. New demands maybe not fulfilled by ITS 90. If that pops up, they have to discuss that. In general, the uncertainties of a new scale must be smaller than of T90. And the ban of mercury, I would say, is a minor problem that can be solved also via an amendment. If we think about the transition from a temperature scale to direct realization of thermodynamic temperature, it's even I would say, a long-term perspective. T90 is NTXX must be faster, cheaper, and in most ranges small uncertainties, even though for the thermodynamic temperature, this is the quantity of interest in general. And there might be some simplifications in a few temperature ranges, but the criteria here for transition from temperature scale to direct realization of thermodynamic temperature must be that we need now reliable primary thermometers and contact thermometry from 400 Kelvin to 1000 Kelvin. The primary thermometers must be realizable not only by NMIs. The uncertainties of thermodynamic temperature measurement must be comparable to ITS-90 temperature, and the effort and the price of such a calibration must be comparable. Okay, so here my summary. So the redefinition has no immediate impact on the ITS-90. Actually, the best way for the user is to calibrate a thermometer according to the ITS-90 and then use the estimates T minus T90 to get access to thermodynamic temperature. We can improve that access by new consensus values from 4 Kelvin to 303 Kelvin, but we urgently need new data above 400 Kelvin. A direct realization by primary thermometry without reference to the triple point of water is at the moment, in the near future, only possible below 2 Kelvin, and it might be possible below 20 Kelvin, but not in the core range of the ITS-90. And innovation is always possible with further development of primary thermometers. We have to work on that and see if we can include further primary thermometers in the mise en pratique. But this is my last sentence, and something I really want to emphasize, that the urge for innovation doesn't depend if it's the ITS or the thermodynamic temperature, must always include a view for the incredible quality of existing ITS and the outstanding scientific work behind it and its forerunners. And that brings me back to my one of my first slides, and I really want once again emphasize that it was brilliant work by Chapuis and all the scientifics in that field. So thank you very much for your attention.